Hello, everyone. Today, we're diving into a topic that honestly trips up a lot of engineering students and professionals alike. But trust me, it is absolutely fundamental to understanding electrical machines. We are talking about transformer resistance and reactance.
Welcome to KognitoKey. I am so thrilled to have you here today. If you've ever looked at transformer math and just felt completely overwhelmed by all those primary and secondary values floating around, please don't worry. In this explainer, we're going strictly by the source material to completely demystify these calculations. We're going to make them incredibly easy to grasp.
Here is our quick roadmap for today. 1. Transformer resistance and reactance. 2. The transformation ratio, K. 3. Transferring to the secondary side. 4. Total equivalent values. And finally, 5. Calculating load voltages. Let's get right into it.
All right, Section 1, Transformer Resistance and Reactance. Think of a transformer as essentially two separate electrically isolated windings. Now, every real-world transformer has some natural resistance in its copper coils, right? We represent the resistance of the primary winding as R1 and the secondary winding as R2. As current flows through, this internal resistance naturally causes some voltage drops on both sides. But listen, resistance is not the whole story. We also have to deal with reactance, which is represented as X1 for the primary and X2 for the secondary. Because these two sides are separated by a magnetic divide, trying to calculate the total voltage drops across both of them at the exact same time is a very messy, complicated math problem. Which brings us to Section 2, the transformation ratio, K.
So how do we actually bridge that gap? We need a mathematical universal translator. And that is the transformation ratio, K. As our source material brilliantly points out, to make the calculations easy, the resistances and reactances can be transferred to either side. Literally, by using K, we can mathematically pick up the complex physics from the primary side and just transfer them right over to the secondary side.
Let's see how that works in Section 3, transferring to the secondary side. Let's walk through the resistive drop step by step. Step 1, the primary resistive drop when referred to the secondary side is multiplied by K, so we get K times I1 times R1. Step 2, we mathematically substitute the primary current, I1, which is equal to K times I2. Step 3, when we plug that in, we arrive at our final referred drop of K squared times I2 times R1. Just like that, we've successfully translated the primary drop.
Moving on to Section 4, Total Equivalent Values.
Okay, now we need the total picture. To get the total equivalent resistance referred to the secondary side, you simply take the secondary resistance, R2, and add it to our newly transferred primary resistance, which is K squared R1. And you know what? The exact same logic applies to equivalent reactance. You just take X2 and add K squared X1. It's elegant, it's simple, and it's incredibly useful.
And finally, Section 5, calculating load voltages.
So why do we just do all of this math? To easily find the final load voltage, of course. If we have a purely resistive load, the angle phi is 0, and our equation simplifies beautifully. The applied voltage, V1, equals the terminal voltage V2 plus I2 times the equivalent resistance. But if you have a capacitive load, phi becomes negative. The equation then expands out to V1 equals V2 plus I2 times the quantity of equivalent resistance, cos phi, minus equivalent reactance, sin phi. The math adapts perfectly to the physics.
And that brings us to the end of today's explainer. We've seen exactly how the transformation ratio elegantly simplifies complex, dual-winding physics into single, manageable equations. But here is a thought to leave you with today. If K allows us to transfer values so seamlessly, how do you think these equivalent values might shift if a transformer steps voltage up by a factor of 1,000 for a massive national power grid? Really think about the implications of that. Thank you so much for joining me today. Please make sure to subscribe to KognitoKey and like and share this video if you found it helpful. Keep learning, stay curious, and I'll see you in the next one.